Okay, now after we covered the logistics of this course, let's get to the more interesting parts and talk about machine learning and learn what machine learning is. So, what is machine learning? For that, let's look at some, I would say, interesting quotes. So, one quote is by John L. Hennessy, a former president of Stanford, and he basically said, machine learning is the hot new thing. So it sounds like machine learning is something cool, but of course it doesn't really tell us what machine learning is. So let's see what Bill Gates has to say about that. So Bill Gates said a breakthrough in machine learning would be worth 10 Microsofts. So based on that statement, it sounds like machine learning is something pretty important. So what is it really? I really like this quote by Rana El-Kalyoubi. And she's a co-founder at Affectiva and CEO of Affectiva, which is a company focusing on recognizing emotions from images and videos. I agree. I mean, it can be a little bit of a controversial topic, like to recognize emotions from face images and things like that. But if you're interested, search for some of her interviews, and she makes a pretty good and compelling point why this is actually sometimes really useful. So anyways, what she said is machine learning is a subcategory within the field of computer science, which allows you to implement artificial intelligence. So what this basically says is machine learning helps us to create artificial intelligence. So like she then says, so it's kind of a mechanism to get you artificial intelligence. So machine learning and machine learning and artificial intelligence, they are closely related. And in fact, machine learning was originally created with a desire to create artificial intelligence. So artificial intelligence is much older. It's an older field. And in order to implement artificial intelligence, researchers developed a couple of approaches, and one of the promising approaches was using machine learning. So here, based on this slide, we kind of learned there's a relationship between machine learning and artificial intelligence. Today, back then, I would draw the relationship like this, where we have artificial intelligence and machine learning as a subfield. Nowadays, I would say it's rather like this, where we have the big field of AI, and machine learning is intersecting with AI, because there are many machine learning approaches, applications that I would say are not necessarily AI, and we will see some of them also in this class or in this course. So nowadays I think the fields are of course very closely related, but not, I would say not all of machine learning is AI, but a very large portion of machine learning is actually AI. In any case, let's get a little bit more precise now what machine learning actually is. So in order to explain machine learning, I really like this quote. This is actually a classic that you can find also in most online material or other materials about machine learning. And I guess it's so often used because it's actually really concise and really captures the idea of machine learning. So what Arthur L. Samuel said is that machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. So what we have here, the keywords are the ability to learn without being explicitly programmed. So there's also an aspect mentioning programmed. And here with machine learning, we want to achieve something without having something be programmed explicitly. So what does that mean? Here, so in order to understand the previous quote, I have a flowchart here, or a diagram here to illustrate the traditional programming paradigm. So with traditional, I mean just I would say regular software development cycle. So let's, for the sake of the example, to make this a little bit more, I would say, to visualize this with a concrete example, let's assume our task is we want to implement an email spam filter. Let's say our task is implementing an email spam filter. And we have an email program, and we want to now develop let's say a separate program that filters our spam. And in order to illustrate that, let's walk through it step by step. So if we have an email spam filter, we have some inputs. So in this case, our inputs would be the emails that we want to filter or recognize as spam and not spam. And the program that we want to develop, this is our spam filter. And the inputs, in order to develop the spam filter in the traditional paradigm, we look at the emails. So we, as the programmer, we take a look at these emails and see, okay, what makes them different, or what makes spam email different from non-spam email, and how could we maybe implement some rules to distinguish between them. And that takes actually a lot of work. So we have to read ideally a large number of emails, do a lot of thinking and comparisons to find out what makes them different and what do spam and non-spam email have in common, so we don't accidentally classify something as spam and so forth. But let's say we looked at 10,000 emails, came up with some good rules. We can then write our program, our spam filter, which is basically a bunch of rules, like in traditional programming, a bunch of if-else statements, basically. And this is our spam filter that goes then to our computer. So it's implemented on our computer. The computer itself executes this and then classifies the emails as classify as spam or not spam. So our outputs would be the labels spam and not spam. So that's the traditional paradigm. So how does machine learning now come into play? So how is machine learning related to that traditional paradigm? So machine learning helps us to do this more conveniently or automatically. So the computer now has the role of developing the spam filter. So before, we as the programmer, we developed the spam filter. So again, so this top part is just the same as I showed you on the previous slide. So this is the traditional paradigm. And here at the bottom, so this part, this is basically machine learning. So what do we have here? What's different between the traditional and the machine learning paradigm? So here, notice that we have now the outputs on the left-hand side. Before they were on the right-hand side. And yeah, that's basically the only difference. So we have here a data set that is labeled. Later we will see not all machine learning algorithms are about labeled data sets. Some approaches exist also to work with unlabeled data. The goals are a little bit different. But now let's say we have this approach where we have labeled data. With that labeled data, remember the outputs previously, they were the spam and not spam. So again, here the outputs are spam and not spam. These are our labels for our emails. So we have now a data set consisting of emails and the correct classification, the correct spam and not spam email. And such a data set could be created, for example, by taking a look at your inbox and labeling the emails. Let's say you go through, again, 1,000 emails, you label them. But now, in contrast to the previous paradigm, here, let me use a different color. Here, you developed the rules. So here you developed rules as the program. But now, we let the computer develop the rules. So we have the computer look at the labels, the spam and not spam, look at the emails, and come up with a spam filter here. And it's learning the spam filter. So the computer does the learning work now. So instead of us having a look here at all the emails, the computer now looks at labeled examples of emails and then develops the program, which is, so I should have, so this is the process of learning the spam filter, and what comes out of it is the spam filter. So here, the computer has now the role of learning from looking at examples that we provide. So yeah, that is machine learning in a nutshell, I would say. Let me briefly follow up on the previous slide. So there's a very, I think, important quote by Fei Li. So what she said is, we will not only use the machines for the intelligence, we will also collaborate with them in ways we cannot even imagine. And I think the previous slide may have made it look like that machine learning is there to replace humans, but I think this is not really true. I mean, in some cases, yes, but it's not entirely replacing all kinds of human labor. I mean, there are cases where it makes sense to use machine learning, and there are cases, I think, where it really doesn't make so much sense to use machine learning. For the email example that I showed you or discussed in the previous slide, I think it's really, we are still developing programs that we like to use. So you can maybe imagine in a distant future that some computer is developing or some machine learning algorithm is developing an email program. But I think nowadays we are not even close to that yet. And we have people thinking about, okay, what is good usability? What do I want? What features do I want? And we have programmers designing email applications or email interfaces. However, we can use machine learning to make the life of the programmer easier. So instead of having the programmer to read through 50,000 emails and deciding what is spam and what is not spam, and maybe making bad choices, we can have a computer doing maybe a better job at that and making the life of the programmer easier by developing the spam filter by machine learning. So in that way, we free up the time of the programmer to focus on other things, and also don't have the programmer doing like boring things like reading through 50,000 emails and making decisions what's spam and what's not spam. So in that way, we can use machine learning to enhance certain workflows, not really entirely replace them. Okay, but now back to the definition of machine learning. So if the previous slide was a little bit confusing, where I was drawing the flowchart or the diagram, maybe I can help you making this more confusing. So no, I'm just kidding. So I just want to offer an alternative definition, and this is by Tom Mitchell. So he described the learning process. So the process of learning as follows. He said a computer program is set to learn from experience E. So this is the experience with respect to some class of tasks T. So we have tasks T and performance measure P. If its performance at tasks in T as measured by P improves with experience E, then this is the learning process. So we have some tasks and we learn basically from the experience, and we measure some performance P, and we want to learn from the experience to become better at tasks T, and there has to be some way we can tell that we make progress, and that is the performance measure. And there are many different types of tasks, many different types of performance measures, and the experience itself is basically, in the case of machine learning, like learning from the data. So like I said, this can maybe be a little bit more precise because we have now some letters here. So in mathematics, letters, symbols help making things more precise. I'm not sure if that's necessarily true for that quote, but I think it really defines machine learning or the learning process nicely. So in order to kind of make this maybe more clear, let me give you an example, a hands-on example. So here that is a handwritten recognition example. So what we have is the MNIST dataset. It's MNIST. So that is a data set consisting of 50,000 images, handwritten digits, the digits 0 to 9. And they are handwriting. So if there are 10 classes and they are uniformly distributed, in this case, we have 5,000 images per digit. So here on the right hand side, I'm just showing you an example of each digit. So this is an example of the letter 0, 1, and so forth. And for a human, of course, it's very easy to tell what digit that is. But for a machine, we have to teach it to recognize what it is. So now maybe as an optional exercise, maybe pause the video and think about how this handwritten recognition example maps to the definition by Tom Mitchell, where we have the task T, the performance measure P, and the training experience E. So maybe pause the video and think about it a little bit, and then continue. Okay, after pausing the video and thinking about it a little bit, I hope you have some ideas of what the task T could be. And it's actually just here the handwritten digit recognition. So here it would be the handwritten digit classification. We can also say handwritten digit recognition, but classification is usually the more common term in the field of machine learning, and we will also see exactly how this is defined in a few moments later in this, or in the next video actually. So next, the training experience E. So that would be the 50,000 images, and they are labeled. So they are labeled images. Labeled means, again, that we have the information available in the data set. So we have the images and also the labels 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that we can show the computer the images, but also the computer has the information about the labels to learn to associate a given image consisting of pixels with a given class label. So now the performance measure P, what could that be? And that is maybe something you or we could discuss in a discussion forum. So maybe I suggest you open a new question or new thread on the Piazza forum on Canvas, and then we can have a discussion. Maybe I will let you go first, you make some suggestions, and other students can maybe chime in and discuss what the performance measure P could be. That would be a good exercise to double check whether what your ideas are and what possible performance measures we could use, and maybe what are the advantages and downsides of different performance measures. So that is maybe a good question for Piazza before I provide you with this information. Okay, lastly, some applications of machine learning. We talked a little bit about the email spam filters. So that would be one application, email spam versus non-spam classification. And there are many other examples of machine learning. In fact, I would honestly have a hard time thinking about anything nowadays, any like software or application that is not using machine learning. So maybe another intuitive example would be sorting letters in the post office. It's just related to the handwritten digit classification example from the previous slide. So for example, if we have a postcard with a classic post stamp, then the sender's address, and then the address where it has to go. And there's usually a zip code. For example, I think the university's zip code would be 53704 or something. So let's say you have written the zip code on the letter. At the post office, they receive a lot of letters. They go to different cities and different states. So it would be kind of efficient to have an automatic sorting system. And that is something where you have the handwritten digits, could be computer printed, but also handwritten. And you have a machine learning algorithm recognizing these digits and sorting them. Or another classic example is you have your smartphone and you have like a little camera there. And nowadays you don't have any buttons, but you have just a screen. Usually the screen goes edge to edge, so you just, if I would draw a modern smartphone, it would just be a square with a little circle here for the camera, and it usually unlocks if it sees your face. So there's some face recognition going on. It's also one of the areas I'm working on, my research areas, working on face recognition. In any case, that would be also a typical example of machine learning. There are many other examples. Could go on and on and on, but that is maybe also an interesting thread for Piazza. So maybe on Piazza open a new discussion thread and have a discussion with the other students and maybe come up with some ideas. I will chime in then and maybe provide you with more ideas, or also maybe just discuss some ideas you have related to machine learning, whether it's a machine learning application or maybe not. So maybe that's a cool question for Piazza too. Okay, so in the next video, we will talk a little bit more about the different categories of machine learning.